Welcome back to NE 630, the nuclear reactor theory class. So last time we tried to seek a solution for the Eisenhower equation, and we showed that we have 7 roots for the equation. We discussed the 3 different situations where rho, which is the reactivity, is positive, 0 and negative, and we clearly stated that when the reactivity is positive, we have a positive root and 6 negative roots. All of them will decay out, and you will have an exponential increase of the reactor power, or the neutron number of neutrons or neutron population inside the reactor. When you have rho is equal to 0, you will have a constant e to the power of 0, which is the first root, and the rest of the roots again will be negative, so they will decay out, and you will reach to a steady state, which is the critical situation. On the opposite side, when we have rho less than 0, all the roots will be negative, with the exception of the first root will be the smallest one. So it will have the period of the reactor will be governed by the smallest root, and in this case, if rho is very large in negative value, we will not be able to shut down the reactor more faster than negative 1 over lambda 1, which is the delayed neutron decay time for the first group. So last time also we tried to discuss the situation when we will have a one delayed neutron group approximation, and all what we did is just average over all the lambdas. So lambda average will be the summation of lambda I beta I divided by beta, and beta is equal to the summation of beta i's. So to continue, the equation for the one group, one delayed neutron group approximation, when we solved this equation last time, we reached to s square minus rho minus beta divided by gamma minus lambda multiplied by s minus lambda rho divided by gamma. This will be equal to 0. Again, last time I told you that this is an equation, algebraic equation of the form ax squared plus bx plus c equal to 0, and you will solve it using the well-known formula for solving the algebraic equation, which is minus b plus or minus b squared minus 4ac all divided by 2a. And we showed that S1, 2 is just given by 1/2 rho minus beta divided by gamma minus lambda plus or minus the square root of 1/4 rho minus beta over gamma minus lambda all square plus lambda rho over gamma. Okay, guys, so those are the 2 roots. So if you plot the equation, the second order equation, you will see that the solution will be like this. And then will be like this. So if you have rho greater than 0, rho equal to 0 situation, this is the rho equals 0, this is the rho greater than 0, and this is the rho less than 0 situation. Again, for rho greater than 0, we will have one root, which is S1 is positive, the other root S2 will be negative. So S1 will be positive, S2 will be negative, and you will have your N of t and C of t will be just e to the power of S1t plus e to the power of minus S2t for both of them. Of course, here you will have N naught 1 and N naught 2, and here you will have C naught 1 and C naught 2. So this term will decay out, and you will end up with what? Exponentially growing neutron population and exponentially growing delayed neutron precursors. So what about the situation when you will have rho equal to 0? I will have what? S1 equal to what? 0, and S2 is also negative, and then you will have N of t is just equal to the initial number multiplied by e to the power of 0 is 1 plus N naught e to the power of minus S2 multiplied by t. Same situation will be for C. So those two terms will decay out, and you will end up with a constant population on time. So if you plot with time, if you plot C of t and N of t, and you start, let's say, the reactor at N naught or C naught, you will have you'll have something like this in both situations. While in this case, if you plot N naught and C naught, C of t and N of t, and you started from here, C naught or N naught, you will have something like this. The third situation, you will have it when your reactivity is less than 0, and this is the subcritical case. And in this case, you will have the two roots are what? Positive or negative? Negative. So you have N of t and C of t will be equal to e to the power of minus S1 of t S2 of t, and let's say this is C naught and C naught. And if you plot C of t and N of t, and you start from a critical situation with N naught and C naught, you will have a decaying function like this. And here both S1 and S2 are negative. Of course, it will not be a simple decay like this. It will be something like this, then this. Can somebody tell me why? So you will have a sharp drop because of the faster decay one. Then you will decay with the slowest decay one. And we will see what's the consequences of this in maybe a lecture or during this lecture. So again, we have the equation dn of t by dt equal to rho minus beta divided by gamma n plus lambda c, and dc by dt equal to beta divided by gamma multiplied by n minus lambda c. And this is coupled first order differential equation. And why it's coupled? Because you have n here, and if you want to calculate n, you have to calculate c. But if you want to calculate c, you have to know n. So it is coupled, and it is first order differential equation. So again, we just stated that we will have two solutions or two roots for each one. If we will assume that the solution will be something like n of t and c of t will be just exponential functions like this. So if you want to play with this equation, so maybe we can write this equation as dc by dt plus lambda c equal to beta divided by gamma multiplied by n of t. And if you assume that your c of t is proportional to e to the power of s t, and same thing for n of t, then if you look here, dc by dt is just, if you differentiate c with respect to t, it will give you s e to the power of st s e to the power of st. And this is nothing more than s multiplied by c of s, as we stated from the Laplace transform of last time. So s c of t s c of t plus lambda c of t equal to beta over gamma multiplied by n of t, and then c of t will be just s 1 and 2 plus lambda equal to beta over gamma multiplied by n of t. So if you divide c of t by n of t, c of t by n of t, this will give you beta over gamma divided by this term here, and this will give you beta over gamma divided by S 1 and 2 plus lambda. And this will give you, from the first equation, this equation here, minus rho minus beta divided by gamma minus S1 and T all divided by lambda. So you can express the delayed neutron precursor concentration as A1 multiplied by n of t A1 e to the power of S1t plus A2 e to the power of S2t, and C of t will be just A1 multiplied by beta divided by gamma S1 plus lambda e to the power of S1t, and this will be A2 multiplied by beta e to the power of S2t divided by gamma S2 plus lambda. So this is just the correlation between the constants in the n of t and C of t, which comes from here. So let's look for, this is just n of t, how the n of t will change with time from the one delayed neutron precursor model, and this is the concentration of the delayed neutron precursor, how it will change with time. So let's take an example for light water reactor. So light water reactor So the beta for light water reactor is roughly 0.0075. Okay, guys? And the lambda equivalent is what? Summation of lambda I, beta I divided by beta for light water reactors. This will be nearly 0.08 second minus 1. And tau, the average lifetime, is just 1 over what? 1 over lambda is tau. Ln 2 over lambda is what? Half-life. So tau will be nearly 12 seconds. And gamma is just 1 over nu sigma fission multiplied by V, and this is 6 × 10⁻⁵ seconds. So this is for light water reactor parameters. So except for the absolute value of rho minus beta nearly 0. What does mean rho minus beta 0? Prompt critical situation. when you have rho equal to beta, you are a Bromwood critical. So except for this Bromwood critical, we have S square minus rho minus beta divided by gamma minus lambda multiplied by S minus lambda rho divided by gamma equal to 0. Okay, guys, look at the values here. Beta is 0.0075. Yes, guys? And what's lambda? 0.08. And what's gamma? 6 10 to the power of minus 5. Look at the two roots. So you have beta. Yes, those are the coefficients. So let's look for the two roots. So one of the roots will be very large, and I will show it to you right now. Will be very large magnitude. So the root is S1 and S2, and I will show you what S1 and what S2. And the other root will be very small. So S1 square will be much greater than lambda rho over gamma. So here we have S1 and we have what? S2. So if the root S1 is very large, it's very what? Very large compared to this lambda rho over gamma. Our equation was what? S square minus rho minus beta divided by gamma minus lambda multiplied by S minus lambda rho over gamma equal to 0. So if the first root S1 is very large compared to this quantity, rho lambda over gamma. So what's rho? What's lambda? Yes? Multiplied by rho divided by gamma. What's gamma? So lambda rho divided by what? By gamma. So this is what? Nearly 0.08 multiplied by rho divided by what? 6 10 to the power of minus 5. So it depends on rho. Rho here will be what? If rho does not equal to beta, meaning that you are the absolute value, your rho is far away from beta, yes? You don't want to make rho equal to beta. So it's not the critical Bromwood situation. So beta is what? 0.075, yes? Rho might be what? Much lesser than 0.075, so that you do not make your critical Bromwood situation. So let's say 0.003 or something like this, half a beta or whatever, 0.003, 0.002. So this will be nearly 2, 3, 10 to the power of minus what? 3. Yes? And here you have what? 8, 10 to the power of minus what? 2. 10 to the power of minus 3 multiplied by 10 to the power of minus 2. This is 10 to the power of minus 5 divided by 10 to the power of minus 5. So, and there is something here in the factor of 8 or 7 and there is here 6, so you will get something like 1-ish. Okay, guys? So this is 1-ish maybe, but this number will be 10,000. So it's too much compared to what? To this number. Okay, guys? So if our root, the first root, is way too much or way too greater than lambda rho over gamma, so we can neglect this term. Okay, guys, for S1. For what? Because if you substitute here with S1, what will happen? If you substitute with a root of the equation inside the equation, you should get 0. So if we say that this is S1 now, and this is what? S1. So in this case, this is S1, this is something multiplied by S1, and this is very small compared to what? S1. So I will take this one term out of the equation, and in this case I will have just S square minus rho minus beta divided by what? By gamma minus lambda multiplied by S equal to 0. I think it is easy to solve. So you will get this with this, and you will have S equal to what? Rho minus beta over what? Over gamma minus lambda. Okay, guys? So again, this term here is something like 10 to the power of minus what? This is 10 to the power of minus 3. Yes, guys? Or maybe 10 to the power of minus 2. And gamma, 10 to the power of minus 5. If you will invert it over, it will be 10 to the power of 5 multiplied by 10 to the power of minus 2. So this is around 1,000. And what's this? Very small. So I can take this one off, and I will say that this S1 will be nearly what? Okay, guys, what's the other situation? We said that one root will be very large, the other root will be very small. So if the root is very small, so we will flip this sign. So it will be S2 is much less than rho small root. So S2 will be much less than what? Square will be much less than rho lambda over gamma. So if your S2 is very small compared to this term, S2 is very small compared to this term. So I can cancel what? The square. Yeah, this is square with respect to this, assuming that this term is much larger than lambda, and this is what we already saw, that this term is much larger than what? Lambda. So I will end up with what? With this multiplied by S equal to this. Yes, guys? And this will give me what? Minus rho minus beta over gamma multiplied by S minus rho lambda divided by gamma equal to 0. So this term is way larger than lambda. I will cancel lambda or neglect lambda with respect to this one. S2 is way smaller than this term, so I will cancel S square. So this will be negative rho minus beta divided by gamma multiplied by S minus lambda rho divided by gamma equal to 0. So in this case, S2 will be equal to what? Lambda rho, gamma will cancel out with gamma, divided by rho minus beta, but you have a minus sign. So when you multiply the minus sign here, it will be beta minus what? Minus rho. So this is the S2, and the S1 is what? Rho minus what? Rho minus beta divided by what? Gamma. So just if you want to get a feeling, let's assume that, I do not know if I have it here in the question or not, but we'll see. Let's assume that rho is half beta. Half beta will be what? 0.00337. So let's say 0.0038, something like this. So what's S1? S1 will be what? Will be something like 0.0038 minus 0.0075 divided by, what's gamma? 6 10 to the power of minus 5. This will give you 3.8 10 to the power of minus 3 divided by 6 10 to the power of minus 5. So this will give you what? 10 to the power of 2, and this will give you half. So this will give you 0.5 10 to the power of 2, something like 50 or so. Okay, guys? And what's this? What's this? It's 0.08. So this is 8 10 to the power of minus 2 multiplied by rho is 3.8 10 to the power of minus what? 3 divided by, the difference is what? The difference is 3.8 10 to the power of minus what? 3 again. Yes, guys? So this will end up, this goes with this, and this will give you 0.08. Yes?
Is it the magnitude of S1, or you just leave that negative?
Yeah, if you take the magnitude. So if it is negative or positive, but I'm just showing you. So this will be 100 or so, S1, and S1 square will be what? 10,000. Yes? And this will be what? 0.08. So one root is very large, one root is very small. Okay, guys? So if you look at the neutron population, it was just n of t equal to a1 e to the power of s1t plus a2 e to the power of s2t. How we will obtain a1 and a2? Initial conditions. Yes? Yes, guys? So you have to solve the initial condition for this one, and the other equation for C1 and C2 we already substituted for the value of C1 and C2 in terms of what? A1 and A2. So you have two equations and two unknowns, and you have the initial condition is N naught and C naught. Yes? So you can solve those, and you will figure out that A1 is just nearly N naught multiplied by rho divided by rho minus beta, and A2 is nearly negative N2 beta divided by rho minus beta, where N naught is the initial neutron population inside the reactor. So in this case, N of T will be just N naught multiplied by rho divided by rho minus beta, e to the power of rho minus beta over lambda over gamma T minus beta divided by lambda gamma e to the power of minus I'm sorry, beta divided by rho minus beta e to the power of minus lambda rho divided by rho minus beta T. This is S1 and S2. Yes, guys? Rho minus beta over gamma is this one, and lambda rho over rho minus beta is this one here. I make it rho minus beta, and I got this, the negative sign out. Okay, guys? And then C of T will be just N naught multiplied by rho beta divided by rho minus beta all square e to the power of rho minus beta divided by gamma to the power of T plus beta divided by lambda gamma e to the power of minus lambda rho over rho minus beta all of T. So those are the two equations from the single delayed or one delayed neutron group approximation. You have two exponentials. When we have 6 delayed neutrons, we have how many exponentials? 7. When we have 1, 2. So if we have 2 delayed neutron groups, we'll have how many exponentials? 3, and so on. Okay, guys? Now, at t equal to 0, this is 0. So this would be what? 1. And this would be what? 1. So C naught would be equal to N naught. And you will have rho beta over rho minus beta square plus beta over lambda gamma. If you unify the numerator, denominator, and then play with this, you will get the initial condition for C, which is C naught, and I will show it to you in a minute. And this will be a function of what? C naught will be a function of what? So at t equals 0, what's the initial condition for n at t equals 0? N naught. And C at t equal to 0 will be equal to what? C naught. But what's C naught from here? If you substitute and solve this equation, it will be beta multiplied by N naught divided by what? Gamma lambda. Okay, guys? To give you a figure of merit, C naught equal to beta is what? 7.5 10 to the power of minus 3 multiplied by N naught divided by gamma. Gamma was 6 10 to the power of what? Minus what? 5. And this was what? 8 10 to the power of minus 2. So let's assume that this will cancel out with this. Yes, guys? And because this is larger than 7.5, there will be a fraction. Yes? Yes, guys? Then let's assume that 1 over a fraction multiplied by 6 will give you 5. So 1/5 will give you what? Almost 0.2. Yes? And this is 10 to the power of minus 3 will cancel out with this, and it will be 10 to the power of minus 2, 10 to the power of minus 2. So this is 10 to the power of minus 4. Go up will be 10 to the power of 4. So this is nearly what? 2000. The actual one is actually 1600 in knot. So what do you think? What's this? What do you understand from this?
C naught is much smaller than M naught.
C naught is what?
C naught is much smaller than M naught.
How? If you have 1 neutron at t equals 0, you have 1600 delayed neutron precursors in the core.
Sorry.
So what this tells you is inside your core, if you start at t equal to 0, you have initial number of neutrons. In note, you will have very high number of what? Delayed neutron precursors inside your what? Inside your core. Okay, guys? Okay, this is from the one delayed neutron what? Approximation. So let's look for a step negative reactivity insertion as a solution for this one group delayed neutron equation. So step negative reactivity insertion. So you have a time t equal to 0, you have rho at time t equal to 0 was 0, meaning that your reactor was critical at time t equal to 0. Then before 0, then at t equal to 0, you drop your control rod a certain amount inside the core, and greater than 0, your rho for t greater than 0 is equal to negative 0.05. So this is 0.008 is the beta. Yes, 008. So this is how many betas? What to multiply by 8 gives you, yeah, 6.5 betas. So you just insert 6.5 betas negatively inside the core. So maybe you drop all your control rods inside the core. So at t equals 0, I have rho is 0, which means that I have a critical reactor. Then I let's say there is an earthquake that took place, and you have the coils that hold the magnet that hold the control rods de-energized because it lost the electricity or something like this. So all your control rods will fail safe inside the core. So they will fail safe and they will get into the core, and you will have negative reactivity insertion like this. So rho equal to negative 0.05 at t equal to 0. So scram, for example, again, if beta is equal to 0.0075 and lambda equal to 0.08 and gamma for the same situation, 6 10 to the power of minus 5. So we will calculate n from the equation that we just solved here, n of t and c of t. So n of t will give us n naught multiplied by 0.87 e to the power of minus 958 multiplied by time t plus 0.13 e to the power of minus 0.068 t. So there is a larger S1 and a smaller S2. And C of t will be just n naught multiplied by 0.0113 e to the power of minus 958 t plus 1563 e to the power of minus 0.068 t. So both of them will be negative. Both of them will be negative. If you plot C of t and n of t here, this is the time, and this is n of t and C of t. N of t, which one will decay faster? The first one. So at t equal to 0, this is 1 and this is 1. 0.13 plus 0.87 is 1. Multiplied by n naught, so you started with what? N naught. Yes? But at no time you lost this guy. Yes? And this guy you will lose how many of the contribution? This plus this give you 100%. If you will lose this, you will lose this factor, which is 87%. So you will lose on no time, you will lose 87% of your what? Of your initial number. So n naught will make something like this. Then you will decay at 13% with this long decaying function. So you will have something like this. Okay, guys? But what about this? This plus this will give you a number, C naught. C naught is n naught multiplied by those two. So you will be C naught somewhere here. Okay, guys? Of course, C naught, as you see, is how many? 1600 times n naught. So I cannot write C naught here, but for the sake of just visualizing what's going on, I will put C naught here. C naught is 1600 times greater than n naught. So I do not want somebody, if I put this in the exam, somebody will come and say, oh, but here it is. You show us that C naught and n naught will start at the same point. This is not true. I'm just for the sake of comparison. So you will start C naught, then in no time you will lose what? A very small fraction, nothing. Yes? So you will not sense the disappearance of this part, and you will decay with what? With a slower decay function like this one. So from the beginning you will have something like this. So this is C naught, and this is n naught. This is, it's called, sometimes they call it prompt drop, and we will see the. So you will go from n naught, okay, to n naught multiplied by 1 minus rho, from n naught to n naught multiplied by 1 minus rho over beta. So this was what? beta minus rho divided by what? By beta. Okay, guys? Okay, guys? Which is the difference between this one and this one? Okay? And this is if you have a negative reactivity insertion. So I will stop here and continue next time. Do you have any questions?
That second one is 1,563?
Yes.
Okay.
1,560. Any questions so far? Okay.